Hello everyone, I'm the proxy presenter of this paper. And if you have any questions, please email the authors. And the title of this work is AutoDCS, Automated Decision Chain Selection in Deep Recommender Systems. And this is joint work between Shenzhen University, Tencent, and Shenzhen Technology University. In real platforms, a user may have multiple types of interactions with an item, such as clicks, collections, and buys. And the last one usually being the target behavior. Multi-behavior recommender systems can leverage knowledge transfer between behavior types to understand user preferences better and elevate target behavior's data specificity. From a decision-making perspective, different types of behaviors reflect users' different level of decision-making considerations and are potentially related to the decision-making of target behaviors. We refer to the dependence of a user's target behavior on the decision-making knowledge of different behavior types as a decision chain. According to the degree of dependence, including all behaviors, partial behaviors and single target behavior, we can divide the decision chain into full decision chain, partial decision chain, and direct decision chain. Most existing work on MBRS indiscriminately use various types of behavior interactions when modeling and predicting target behaviors for each user. And this is they follow a full decision chain constraint. However, we argue that this constraint may be too strict in practice because it ignores each user's unique decision dependence. This motivated us to propose an effective and efficient decision chain selection framework for MBRS to bridge the gap. And for ease of description, we first gave the problem definition of multi-behavior learning using necessary notations. And this is overall our AutoDCS framework, and it consists of 4 steps. The first is the embedding initialization, and we use one-hot encoding and embedding table to generate embeddings for users and items. The obtained initialization embedding will be used as the input of the base cascade module. In the base cascade module, we take the concise implementation of MBRS based on the cascade graph paradigm as an example. And we use Xian as a concrete implementation of a graph convolution. And the specific propagation and aggregation process are shown in Formula 2 and Formula 3. And note that the embedding of the previous behavior will be directly used as the input of the graph convolution model of the next behavior to form a cascade. The obtained behavior while using embedding reflect the user's decision-making knowledge on different behavior types to a certain extent. To identify the importance of different types of behavior knowledge in triggering the target behavior for each user, and we use a user perspective gate to measure the contribution of this behavior knowledge, as shown in Formula 5. Selecting the decision chain corresponding to the current user based only on the user perspective gate means that user will follow the same decision-making pattern when performing target behaviors on all items. To elevate this problem, we further introduce an item perspective gate driven by the item embedding, similar to the user perspective gate. To optimize the proposed bilateral matching gate, a straightforward idea is to multiply them directly with behavior-aware embeddings and introduce them into the model training. However, this direct coupling may create training difficulty. We propose equally each behavior with an additionally behavior-augmented embedding and associating gates with them. Then we selectively activate the corresponding behavior-augmented embedding based on the obtained bilateral matching gates. And in embedding aggregation, we directly combine the original behavior-aware embeddings and behavior-augmented embeddings with different activation states. And finally, the module prediction is defined as the inner product of the final user and item embeddings. And we use the standard BPR loss as the objective function in our experiments. And in the experimental part, we choose 4 public datasets: Tmall, Beibei, Taobao, and JD. And we select a competitive set of MBRS methods as the baselines, including single behavior modules and multi-behavior modules. Among them, CR GCN, MBC GCN, and PKF will serve as a stronger set. And here are the implementation detail of our framework and baselines. And this is the main result. And the method based on the cascade graph paradigm shows better advantages among our baselines, illustrating the necessary of considering user decision-making patterns in multi-behavior learning. And our AutoDCS consistently outperform our baselines. And this shows that it is beneficial and necessary to accurately consider each user decision-making patterns in MBRS. And to analyze the contribution of some key steps in AutoDCS, we conduct an ablation study and reported the results in the table. And we can observe that removing or replacing different key steps affect the model's performance to varying degrees. And the variant that removes the decision tree selection mechanism significantly decreases. And next, we control the multi-behavior information in the experiments to measure the impact of two key factors on our AutoDCS, including the number of available behaviors and the order of behaviors considered during modeling. And we can observe that wheel and add-to-cart behaviors are more likely to be useful in capturing user decision-making patterns, and then collections and incorrect cascade paths usually have a certain impact on the model's performance. And to verify the compatibility of AutoDCS in MBRS, we integrate different cascading graph-based MBRS methods in the beta cascade model. After integrating our AutoDCS, we can observe that all cascade graph-based backbone models significantly outperform that origin version in all metrics. And next, we conduct an analysis to answer whether our AutoDCS can capture different user decision-making patterns. And as shown in the table, in addition to the full decision chain, the C4, and our AutoDCS can identify different decision-making patterns for different users. And by dividing users into different groups according to the decision chain pattern, we observe significant performance gains in our AutoDCS for both users employing the full decision chain and those using a non-full decision chain. And finally, we give a brief summary of this work on this page. And the codes and slides are available at this link. And if you have any questions, feel free to contact the authors. Thank you.
Okay, thank you to the speaker.